Okay, so now we can actually carry out the renormalization of our theory. If you remember previously, we obtained some matching conditions. The difficulty with using those matching conditions is that infinity started to appear. Well, now we know how to regularize the theory and get finite answers. So let's use that knowledge to actually get three well-defined matching conditions or normalization conditions that allows us to make sense of the theory. So what were our matching conditions? Well, remember that we said the Fourier transform of the two-point function must have a residue equal to I, and it must have a pole at the physical mass squared. Well, that gave us a couple of equations. I'm just going to remind you of those equations. I'm not going to rederive them. So the first equation was z is equal to 1. Let's call that equation 1. And this fixed the residue to be equal to 1. The second equation told us that the physical mass squared had to be the pole of the two-point function, and this was equal to m squared plus 12 ig, the integral d4k over 2 pi to the 4, and then we had I over k squared minus m squared, and now I'm going to say plus I eta, because now we use epsilon to denote 4 minus the number of dimensions. Okay, so we used epsilon to say, you remember we said d is equal to 4 minus epsilon dimensions. So I don't want to use epsilon again. Eta is just some infinitesimal number that tells me how to shift the pole, so no problem there. So if I now use dimensional regularization, you know exactly how to do this. We discussed this example. We'll find mp squared is equal to m squared minus 12g m squared over 4 pi squared multiplied by 2 over epsilon minus the log of 4 pi m squared over mu squared minus gamma plus 1 plus order epsilon. And I just wanted to indicate that there is order epsilon. We really don't have to care about those order epsilon terms, but let's not forget that they're there. We'll call this equation 2. So this is our second matching condition. What's important to recognize here is that the physical mass squared is finite and it's some definite value. This is what is measured, okay? So we could actually set the physical mass squared equal to some number. But notice something. As we take epsilon to 0, well, here there's a divergence. Because we've got that divergence on the right-hand side, but we know that the sum of all of the terms on the right-hand side have to be finite, it means that actually more terms on the right-hand side must also be divergent so that the sum in the end is finite. So this means, in fact, if you analyze this equation carefully, m and g must be divergent. That's the only way that we can cancel out the divergence from 2 over epsilon. So m and g would be divergent parameters that you don't care about anyway. You never measure them. And they would be infinite in such a way that this right-hand side of equation 2 is finite and equal to the measured value. Now, this point of view is the point of view that would be taken by Feynman, Schwinger, and Tominaga. I should tell you that Wilson had a different point of view, I think a more compelling point of view, And we'll be exploring that in the next chapter. But for now, let's stick with Feynman, Schwing, and Tominaga, and we would say that M and G must be divergent. Apart from the physical mass squared, we've also got the physical coupling, and this too must be finite and measured. What is the physical coupling? Well, we've got an equation which says minus 4 factorial I GP, and we found that this was equal to minus I 4 factorial G times by Z squared. And then we had plus V of P1 plus P2 plus V of P1 plus P3 plus V of P1 plus P4. I'll tell you what this function V is in a minute, but let me just say for now that we also had to evaluate this equation at a very specific momentum. So we wanted P1 plus P2 plus P3 plus P4 to vanish, okay? This was the condition of energy momentum conservation. We also wanted each of these, Pi squared, to be equal to the physical mass squared, so MP squared. And we also wanted P1 plus P2 squared to be equal to 4 times the physical mass squared, and P1 plus P3 squared to be 0 to be equal to P1 plus P4 squared. Good. So this was the condition. And now let me tell you what V was. Well, I'm going to call this equation sitting over here, equation 3. That was our third matching condition. And you need to know what V of P is. And we evaluated this in dimensional regularization as well. So V of P is equal to, so it was minus I G Z squared squared. And then we had a 4 factorial squared for each vertex. And we had over 2 for equivalent lines. And then we had the loop integral over the loop momentum that I've called K here. So d4K over 2 pi to the 4, we had an I over K squared minus M squared, I'll write plus I eta, and then I over K plus P squared minus M squared plus I eta. This was divergent, but we regularized it. And the answer after regularizing was 288 G squared Z squared over, oh, let me put in the Z to the minus ones, okay? 288 G squared Z squared over 4 pi squared. Then we had the integral over the Feynman parameter, so from 0 to 1 dx. And then we had 2 over epsilon minus the logarithm of m squared plus x into, it was x minus 1 p squared over mu squared. It was minus gamma plus log of 4 pi, and then plus order epsilon. And you see once again that here there was a divergence. Look, there's 2 over epsilon. As we let epsilon go to 0, we will get a divergence. So again, to cancel this divergence, G and M had better be infinite, okay? Now, what kinds of things do we want to do? So we're going to use these matching conditions. So we're going to use equations 1, 2, and 3. They're now well defined as long as we don't set epsilon equal to 0. We are going to use 1, 2, and 3 to eliminate Z, M, and G from the theory completely. And we will replace them by the physical mass and the physical coupling. Okay, so that's what we want to do. And a very natural question to ask, and this is what we're going to ask, is using only these three equations, 1, 2, and 3, are all divergences in the theory removed? That's the first question. Does this remove all divergences? And if the answer is yes, then we say the theory is renormalizable. I should really stress once again that we're thinking just like Feynman, Schring, and Tominaga. We're really going to take a different point of view in the next chapter. Wilson's point of view. And Wilson's point of view, I think, is the better one. So another natural question, very natural question to ask is, how do we determine if a theory is renormalizable or not? So that would be a nice thing for us to determine. Okay, so first an observation. So I want to summarize what is the content of condition 1 and condition 2. So I really want to understand what they're telling us. And what they're telling us is the following. Okay, so first of all, I should say these are the questions that I want to answer. I'm going to be satisfied to work to one loop only. You could easily check yourself by going to higher loops that the answers that we obtain do carry over to higher loops. A lot of the work in proving that a theory really is exactly renormalizable is proving that the analysis that we are going to do here at one loop can be carried through to all loops. So it requires sophisticated combinatorics and a lot of mathematical reasoning. And I don't think that you get much out of it, okay? You don't get much in the way of physics. So we're not going to bother to do that. I'm just going to show you how renormalization works at one loop. And then in the next chapter, we'll think like Wilson does. So what is the content of 1 and 2? Since we're only working to one loop, if we were looking at the 2-point function, we would add this diagram to that diagram. Now, what is interesting, this diagram over here is I over p squared minus m squared plus I eta. So it already involves divergent quantities. So it involves divergent quantities. And that means ill-defined quantities. And this integral, we also know diverged. So both of these terms were badly behaved. And let's denote this sum by a double line. What's the content of these conditions 1 and 2? Well, when you've added these two, the content is that this sum is equal to I over p squared minus the physical mass squared plus I eta. Okay, and now everything is well defined and finite. So that is remarkable. In general, if we were studying the theory to higher loops and or maybe a theory with different interactions, we'd still get an answer like this. But the numerator, for example, might be some function of momenta, and the value of that function at the pole would be fixed to ensure that the residue is I. This particularly simple form for the 2-point function in momentum space only occurs because phi 4 is so simple. In general, you would be able to have, so let me just write down what you'd have in general. In general, you'd have some function of p sitting at the top here. Okay, something like that. But the residue would still be I and the pole would still be at mp squared. When I say that phi to the fourth theory is particularly simple, it just means that possible p dependence that we could have had is actually just a constant equal to 1. So that's what the 2-point function looks like. Good. Okay, we will continue in a moment.